as always, if you ask me a question, your voice will be heard. So let's have a look at this. So previously we talked about how there were two types of charges, positive and negative, and good old basically Millikan, using his oil drop experiment, was able to find the smallest amount of charge, which was 1.6 times 10 to the minus 19 coulombs, and we spread the charges around on an insulator, and they stick at very specific locations, and they won't move around. If we put them onto an isolated conductor, they will nicely redistribute themselves, but still be trapped. So we tend to do that. We spoke about basically having electrostatic forces, and we looked at them in two ways. We looked at them just looking at the magnitude, and we figured out, just like really Galileo did, how you figure out the magnitude of these charges, of these forces. And then we spoke about how we can do this in vector terms. And my plea to you was, don't remember any like magic formula for getting the sign or the direction of these things. Look at your diagram and let that diagram guide you through it. We did a couple of examples of those, and then we looked at some conceptual questions about having a couple of charges. And then did we get to here? I think this was about as far as we got. Is that right? I think this is about as far as we got. Yep. So what's going on here? What's going on here is, let me get my pen up and running. Yeah. So what's going on here is we have a series of charges. We have, 1, 2, 3, 4, 5 charges, and they're basically affecting each other, but the one that I'm interested in is this charge Q. I could do this same question and ask you about charge big Q2. I could ask you about charge big Q3. You'd draw different arrows, you'd have different vector magnitudes, you'd have different vector directions, but it's in principle the same problem. And the idea is that there's always a net force on something. Particles or charges, they don't get stretched. They basically just feel one net force, like a billiard ball. And so you vectorially add all these other forces. So Q2 causes a force, and Q1 causes a force, and so on. So these forces are being caused by these different neighboring charges. One of the most common misconceptions is people tend to think that if I know the force caused by Q1, in the isolation, when there's no Q2, Q3, Q4, and then I have a Q2 added, somehow the addition of this component, this charge causing this force, somehow detracts or adds to the force F1. It's a bit like attention. If I'm listening wholeheartedly to you, I can't possibly listen wholeheartedly to you and somebody else. I've got to split my attention. And so there's this instinctive feeling that somehow when you get more and more charges, you get less and less influenced by that original charge. That original charge is completely unperturbed by the additional charges. All that happens is that the charge Q has a lot more forces acting on it. But the proximity of Q2 does not affect the force caused by Q1. So in a way it makes life very simple. You just work out the forces caused by each pair, Q and Q1. Work out the force by Q and Q2, the force by Q and Q3, the force by Q and Q4. And then when you've done all that, you add them up vectorially. It's really quite nice. Can I just ask you a quick conceptual question? Q1, if Q is positive, what charge is Q1? Got to be the opposite, hasn't it? Because it's an attractive force. And Q2? What charge is Q2? Got to be positive, hasn't it? Because it's pushing away. What about Q3? Negative. What about Q4?
Positive.
Q4 is also going to be negative because it's attracting, yeah? So just a little aside there. So how do we write this? Well, we say that really F net, our net force, is equal to the sum of all these individual forces. And so for each one we say, what's its magnitude? So we have its magnitude given by that. And then what's the direction? And the direction we really get from the diagram, don't we? We look and we say, what's the displacement vector from Q to Q3? And then we normalize that, and that's that vector we use. What's the displacement vector from Q to Q2? Well, we can work out what that direction is, normalize it. We've got to remember it's in the opposite direction. So there's these various games we can play. What they tend to do, what the book tends to do, is it gives you this kind of problem with a lot of symmetry. And I got mixed feelings about it because it looks very complicated when you first see it, but once you see the pattern, it's actually a really easy question. So it tends to be one of these things where if you've never seen it before and you see it in the test, you're kind of like flummoxed. And if you've seen it before and you see it in the test, you're kind of like, it's a lot easier than you'd really like. But this is a very common question, so I don't want you never to have seen it before. This says 4 equal positive charges. Where are these charges? Well, X, Y, Z and W, these 4 charges. They're positive charges. I didn't put the positives on, but you can put the positives in. So they're pushing away from each other. Lay at the points illustrated in the diagram. The magnitude of the force experienced by charge X is charge X. Because of charge Y, there's charge Y. So I'm looking at this bit here now. I'm talking only about that. Is 3 newtons. Well, they're both positive, so this force is going to be 3 newtons like that. That's not the question. That's just a piece of information. Then it says, what is the magnitude and direction of the force experienced by charge Z? Oh, so it's not even like I'm going to use what I just did in any great detail. It was just an illustration to give me a scale. I'm interested in the magnitude and the direction of the force experienced by charge Z. So charge Z will be pushed away by charge X. It will be pushed away by charge Y. And it will be pushed away by charge W. Now, if we look at this, between Y and X was 2 meters, and you got a 3 Newton force. Well, between X and Z is 2 meters, so we'll get a 3 Newton force. And between Y and Z was 2 meters, so we'll get a 3 Newton force. And between W and Z was 2 meters, so we'll get a 3 Newton force. So again, you know, it's like it's pretty straightforward once you realize what they're telling you. Now it asks for the magnitude, that's the size, and the direction. So the kind of logical thing to do, if I can change the color of my pen, it would be really nice. Let's try it. So can I change the color of my pen? Yes. So let's go ink color. Let's go to a nice, I don't know, a nice green. So I'd really like to this is now vectors. Let's break this up into a X component, a Y component, and an X component. Dot, 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 dot. Remember this from physics 1. And a Y component and an X component. Dot, 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 dot. And then I need to have an angle. Let's do the angle to the horizontal. So can somebody tell me what is the expression for that vector there? What would I say in threes and thetas? What would it be? It would be 3. Which one? This guy here, the one on 3 sine theta. And this will be 3 cosine theta. Yeah. And then this guy here would be another 3 cosine theta. What about this guy down here? Minus 3 sine theta. Okay. You can see immediately that plus 3 sine theta and that minus 3 sine theta just cancel each other out. I suppose I need to know what theta is. Can you look at the diagram and can you tell me what angle theta is?
60 degrees.
It's 60, isn't it? And how do we get that? It's 60, 60, 60. So that's going to be an equilateral triangle, is it? So that's going to be cosine 60 and sine 60. So my components are these guys. And they're all pointing in the positive x direction. So my magnitude is equal to 3 plus 3 cosine 60 plus 3 cosine 60. So this is going to be is equal to 3 plus 1.5 plus 1.5. So my force is going to equal 6 newtons. And it's pointing to the right. So it would be what answer? A would be the answer. So what's my feeling about that? In a way, it's a little bit too cute, you know. It's like it's relying too much on symmetries. It's not really testing whether you know how to use that superposition principle in a big way. It's really testing, did you spot the symmetries, you know. And it's just, you do see them. They like that question in the kind of textbooks. It's a traditional question. Could you express that to me as IJK notation, assuming that the page is, you know, X is horizontal, Y is vertical? How would I write this in IJK notation? It'd be something I, something J, something K. 6I plus 0J plus 0K. And what have I missed? Yes. Just because you put a whole bunch of IJKs down does not mean to say it doesn't need units. It needs units. So that's a IJK notation of the same thing. Okay? So not bad. It's just a little bit, I think it's a little bit clever. You know, it's like, oh, man, okay, this is not really about what I thought it was going to be about. This is really about vectors and all that kind of stuff. You know. So I want to try and convince you that forces are great, but we really need to work in terms of fields. And is this from your class? From last time? I think someone's been here before, probably the other class. So here I have a little, let's do just another page. Okay, because we're going to do something similar. So here's the deal. When we do our point sources of charge, and we try and ask ourselves what the force is acting here. It's a bit like going on a holiday and looking at, you know, 3 mountain tops. Now, in reality, you might want to go on a little hike in this area here, and maybe your map, well, let me ask you, does your map need to contain all the mountains, mountain tops? If you go to the Smoky Mountain National Park, do you need to have a map which has every mountain top on it so you can figure out what your hike's going to be like? Or is it sufficient to have a local map with contour lines on it? Yeah, you don't need the map of everything. You need just the map of where you're going to be. Because frankly, we know that mountains kind of look like this. You know, didn't do that very well, but I'm making it up as I go along. These are different height contours, and you know, if your journey is taking you along this bit, then, you know, well, I climb out of the valley and I go back into the valley and I climb up the other side of the valley, you know. I don't need to know where the mountain tops are. All I need to know is what's going on where I am. If I have a couple of contour lines on here, I can pretty much figure out what I need to do. So after a while, you don't care about the mountain tops. All you care about is your local contour lines. And rather than saying, well, how much work would it be for me to go on this hike, compared with how much work would it be for my daughter to go on this hike, I can just talk about the change in height and the topography, and we can figure it out. So we go away from actual forces and we start talking about a measure of the strength of the gravitational pull and, you know, how much work we're doing against it and the like. We become a bit more abstract, but we get very used to it. I mean, a contour map, we don't really care how many feet we have to climb. What we care about is how hard is it. And we look at the number of feet we have to climb and we interpret it, you know. It's like, so we get used to looking at a quite abstract thing and getting real information out of it. And what I'd like to get you guys convinced about is that, you know, you can get really complicated systems and you'd have a really tough time working out the physical consequences of all those charges. But if I could just get the local topography, it's fine. Let me give you an example. So I used to work for an electron microscope company, and they would make electron guns. Electron gun is basically a hairpin of tungsten, and you heat it up so that it's glowing, and because of the tip, high electric field means a lot of electrons are given off, and they tend to go off like that. The tip is quite broad because you want a fair amount of heating, so that it's almost like having a wide light, a wide source of electrons. And you'd like to try and pinch that source down so that it appears much more defined. And so you get what's called a Wiener cap, which is basically a piece of three-dimensional metalwork, which is a bit like, it's like a nozzle, and it screws over the tip. And this is, if you looked at it, this would look like this. So the electrons would come out of here, and this shape here is that flange there. And what it's doing is, if I imagine this is the source, the electron wants to go in that direction, but because of this electric field, it kind of forces it back and it goes down there. And this other electron wants to come around here, but because of this electric field, it forces it across there. And all these guys get focused through the same point. And so this is your virtual source. So you have a virtual source here where all these electrons cross over. And by really being careful, you can control this and make it very well defined. You can make a really nice, sharp focal point on this. Well, can you imagine trying to work out what the force on an electron is at a point here, at a point somewhere in here, caused by some, you know, all those charges on this array of atoms, and there's all the charges down here. I mean, that's how you do it. You charge this thing up, you put a voltage on it. So that would be a pain. What they do is they say, let's make a map of it. So they literally make a kind of, let's see if I can remember what it looks like. It's going to be a map where it kind of looks like that. And then here it looks like that. So they design a very specific contour map And they do it very carefully. They use computer simulations, and then they'll go and build it and test it and all that kind of stuff. There's a lot of technology in that. Very complicated stuff. All made much easier by electric fields maps rather than trying to work out electric forces. So in our life as studying electrostatics, then the divisions are we looking at the force, or are we looking at the field? And then another division is it uniform? That means like inside a parallel plate capacitor, or is it radially symmetric? And this is actually even more complicated, you know. But that's what the things we look at, you know. It's basically what's going on. So let's get out of here. And that's what we're talking about here. What we're going to say is, okay, look, the electric field can be considered as an aura that surrounds a charge and is a storehouse of energy. So we have is a charge. And like gravity spreads out around a planet or any mass, so around a charge we have an electric field. We say that gravity always points, the gravitational field, little g, always points towards, you know, the mass, yeah? Our gravitational field points downwards, the big mass, I guess I should say. Then in this case, then our electric field, it's more complicated because we have two types. We have positive charges and negative charges. So we say that the electric field, pick a point in space, the electric field will go in the direction of a positive charge if you put the positive charge there. So if this is positive, the electric field would be in that direction. Now remember, on a map, you can have contours and you can pick any point in that terrain and ask questions about it. You don't have to have a mountain top and ask questions about the mountain top. That's what we've been doing kind of so far. One mountain top is at this vector, another mountain top is at that vector. Here's the vector between the two of them. What's the force felt by that mountain top? It's that. We're only looking at the peaks. We don't have to look at the peaks. And so by going from having two charges and saying what's the force on this guy, I can go to having one charge and say what would the force be on this guy if I happen to put a charge there. And that's what field's about. What would the force be? So we invent this thing called electric field, and we say the electric field strength at a point in space, not a charge, but at a point in space, is numerically equal to the electric force that would have been experienced by a unit positive charge at that location. So if I have a point of interest, here's my point of interest, I say, well, I can figure out the electric field by saying it's the force that is felt by a charge at that point divided by the charge. Here I put down Q naught, and here I'm putting down Q, so let's just put Q naught in. But you know, in reality, that charge is my test charge, and it does not have to be there. So I could say, what's the electric field here? What's the electric field here? What's the electric field there? What's the electric field there? And they all have decent answers. I numerically get the value by imagining putting a 1 coulomb positive charge wherever I have an interest. But I don't have to have that second charge there. I don't need to be stood in the mountains for the map to have a contour line on it. Yeah? So I don't need that second charge. I just need the original charge. I have a definition, and it says that my electric field is equal to the electrostatic force divided by the charge at the point of interest. So here's my big Q. That's not the Q I'm interested in. That big Q causes that Fe. And when I divide that Fe, why that big Q causes that Fe on this charge here? Well, I know the electric field at this point where this little charge is by dividing the force felt by that charge times the charge value of that charge. But in a way that's cheating, because I'm putting a second charge in and saying, oh look, this charge feels 5 newtons, and this charge is 2 coulombs. So my electric field is 5 divided by 2. Or I say, oh look, this charge feels a force of 20 newtons. And the charge is 5 coulombs, so that would be 20 over 5, which is 4 newtons per coulomb. But I put an original charge in there. I put a charge where I'm interested in there to kind of get the answer. But I don't have to do that. Down here, I've got the same situation, but I'm going to say, forget about that charge. I just want to know about this guy. Forget about that force. I just want to know about this guy. And the way I do that is, well, I say, well, okay, what was the force? F is equal to Ke, big Q, little q, over R squared. And I got my electric field by dividing that by the little charge. So let's divide that by the little charge. And that gives me Keq over R squared. And if you look at that, you don't actually need to put in a value for this little charge you put in here. We can just define the electric field at a certain point by knowing what we might call the mother charge, the charge that sets up the electric field that I'm interested in, and knowing the separation, and knowing Coulomb's constant. So there are two ways of getting at the same thing. The field itself is important, but we can define the field in two ways. We can say, okay, let's imagine putting a charge in this point. Let's figure out what the force is and then divide the force by the charge that we put in there. Or we can turn and say, let's just get to the base equation. Oh, the electric field at a point depends upon Coulomb's constant, depends upon the mother charge and the separation between the two. So two ways of looking at the same thing. Electric field, though, is very useful. So to continue this, electric field strength E can have units of newtons per coulomb or volts per meter, and they're dimensionally identical. Do you remember, like, we had impulse and momentum, and they had the same dimensions, even though the units were different? Newton seconds and kilogram meters per second, they're identical things. So a newton coulomb is the same as a newton per coulomb is the same as a volt per meter, and we'll get to that. And then secondly, by substitution and expansion, we see that the separation between the mother charge and the point of interest affects the electric field in an inverse square relationship. And we can see that's an inverse square relationship. By the way, let's just have a look at this. So we said that Fe was equal to Ke, big Q, little q, over R squared. And now we've said that E is equal to Ke big Q over R squared. Whenever things are similar enough that they will confuse you, put them down side by side and look at the similarities and differences. Can you tell me one thing that's similar about these two equations? What have they both got? So Ke is in both of them. So Ke is similar. You'll find in all this electrostatic stuff, Ke is involved. Well, not all of it, but most of it. That's the similarity. What's another similarity? They both contain the mother charge. And then what else is similar? They've both got the inverse square law. Now, what's different? The force needs the charge to be pushed. Remember, forces, two objects, two forces, action-reaction pair. Without that second charge, you don't get any pushing. The electric field does not. And we'll keep coming back and looking at this because we're going to have voltage and we're going to have electrostatic potential energy. And they all look similar. It's all just so close. So we say electrostatic field and electric force. We say a large point charge Q establishes an electric field. And you can imagine it as just like going out in all directions. It's like that. It's just like an aura going away from it. Goes out radially symmetrically, spherically symmetrically. And if we say the force is equal to Q over R squared times R hat, and to the situation we get FEQ, the force on this little charge here, is equal to Ke, the big charge, the little charge over R squared. If we apply E is equal to the Fe over Q naught, then substitution gives us that. That's just a formal way of getting what we had already. What is the magnitude of the electric field at the point 3 meters from a 6 coulomb positive point charge? We'll put positive down. I don't think I'll put positive down there. So 6 coulomb positive point charge. Can you have a go at that for me, please? So draw yourself a little diagram. I'll start you off. So magnitude of electric field at a point which is 3. So I have my 6 positive. I don't bother with the coulombs. Just 6 positive. 3 meters away. 3 meters. And this is my point of interest. And I don't want the force. I want the electric field. So E. So what do I know? E is what I want. Do I know a separation? Do I know a mother charge? Do I know a little charge? And write down your equation. And the way you get these clickers to work is you turn them on, you go on, and then you click whichever letter you think is right. Oh, and the other thing I've got to remind you of is Ke is equal 9 times 10 to the 9 and newtons, can't remember the units, shame on me. No, that's electric field. No, it's going to be newtons coulomb squared per pterodactyl or something. So you got it? I got 4 answers. What is it? Newtons? Meters squared? Per coulomb squared. Thank you. I think that was 3 meters, and I think this was positive 6. I got 5 votes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17. I'm about a third of the way there. If you didn't get a clicker when you came in, get yourself a clicker now. And you just turn them on and you go click. And I don't know, I make no attempt to find out. You've all got random clickers, and I'm happy with that, because this is not a test. This is, I want us all to see how we're doing. And for instance, it's helpful to me to see how long it takes people to make that first cut. Hi. I don't think so. Man, I have the little red thing on as well. So how are we doing? 13 people, halfway there. Come on. What do you think? We've got our list. We need our equation. So, I'm going to stop you in a minute because I need to get a move on. Let's stop. Let's look at most people are saying C. Let's have a look. I'm going to move this to one side so I'm going to try and move that to one. Oh, maybe I can't do that. Okay. So let's have a look. So the equation that links these things is E is equal to KEQ over R squared. So E is equal to 9 times 10 to the 9 times Q. Q is 6 over 3 squared. E is equal to 9 times 10 to the 9 times 6 over 9, which equals 6 times 10 to the 9, and units. Let's have a look. It's going to be newtons per coulomb. So 6 times 10 to the 9. Yay! Great. Electric field, yeah. Newtons per coulomb. Or volts per meter. Newtons per coulomb or volts per meter. Force per unit charge. Yeah. Newtons per coulomb. So not bad. Let's move on. I've got to do it there, haven't I? So come down here. So, and here we have it again. We say, look, you can have a whole bunch of charges, and now we don't have a charge in the middle. We just have a point in space. This is just a point in space. And now can you tell me, if the electric field is pointing up and to the right, what is this, positive or negative? What is this? Is this a positive charge? That's a positive charge because it's pushing. If you were to put a positive charge in here, it would be pushed that way. And what would this be, positive or negative? It's attracting the electric field, if you like, so that must be a negative. Negative, negative. So we can infer conceptual things. And again, this is electric field net is equal to the sum of each individual electric field, which equals, you know. And what do you think the next page is going to look like? Oh man, we've been here before. Let's have a look. 3 equal positive charges, yada, yada, yada. So we don't have 4 now, we have 3. That's positive, and that's positive. And let's have a look. The electric field here would point in that direction. If we imagine putting a positive charge there, electric field would be in that direction. Electric field would be in that direction. Those are my 3 electric fields. I can break it up into a component. So I can say, oh, look, there's that component and that component and that component and that component. And we know that's 60 degrees and we know that's 60 degrees. How big are these vectors? It says the electric field at any point that is 2 meters away from any individual charge is 6 newtons per coulomb. And lo and behold, that's 2 meters, that's 2 meters, and that's 2 meters. So that's going to be 6, that's going to be 6, and that's going to be 6. So with that said, can you please tell me what the answer is by clicking in? What would the magnitude, what is the magnitude and direction of the electric field at point Z? So basically you've got to summarize all that. I'm going to neaten up my diagram. Cool. And how are we doing? We've got 7 people. This guy, of course, cancels out that guy because they're equal and opposites. So what's it going to be? I'm going to let go just for another few seconds. I'm summarizing these guys. And let's stop it there. If I can actually find my mouse to stop it. I guess it's looking for a pen. So I'll stop that. And let's go here. And mainly people are saying A. Sometimes people are saying B. So let's have a look at this. So I say, oh, well, my E is equal to, it's going to be 6 plus 6 cosine 60 plus 6 cosine 60. That's those 3. E is equal to 6 plus 3 plus 3. E is equal to 12 newtons per coulomb. And they're all pointing to the right, so A would be the best choice on that. Cool. So let's go from having a whole bunch of discrete charges to having a cloud of charge. So we say, well, look, we divide a continuous charge distribution, that's a cloud of charge, into small elements, these little small cubes of charge. And for each one, we're going to cause an electric field, a little bit of electric field. So we'll call it delta E, the little bit of electric field. And for each one, well, the equation is going to be the same. It's going to be KE, the charge, over R squared. Now, the unit vector will point in the appropriate direction. So if this is a positive charge, the electric field is going to be pointing away. If this was a negative charge, it would be pointing towards. So I've got to do some visualization there. So the total electric field at this point of interest, well, there'd be like little contributions from all over this thing. There'd be little contributions, you know, all these little cubes of charge are going to cause an electric field vector with slightly different magnitude and slightly different orientation. So my total, my net electric field will be the sum of all these guys. And if I got the cube small enough, I would go and say my electric field, my net electric field, was equal to the integral. Let's not call it, you know, delta E's, let's call it dE's. We've gone to the limit. So now we're doing a bit of calculus. And as always, we'll cheat as much as possible by using symmetry. And so my equation, well, KE's still in there. Rather than my little bit of charge, delta Q, I have dQ. My R squared is still in there. And my unit vector is still in there. Man, summing a whole bunch of unit vectors is going to be a real pain. So we picked highly symmetrical examples. So we leave that for the mathematicians to do. We take highly symmetrical examples. And not just, I swear it's not just me. It's the book. If you look at the book, they're always using symmetries to make life simpler. And yet I see sometimes the mathematicians plow through things, you know. And they teach calculus, you know. So consider a rod with a uniform charge totaling 9 coulombs. The rod lays on the x-axis, so here's the rod. And I know my Q, big Q, is equal to 9 coulombs. Let's have a look. It extends from, if that's my origin, extends from +3 to +7 meters. Use calculus to show that the electric field at point P, which is located at +1 meter, so here's my point P, +1 meter, there's my point P, is that value. So I want to change my pen because I want to do some thinking here. So change the color of my pen. Let's go to a red color because this is important, okay? So I'm going to divide this up into slices because that's how I do calculus. And each slice is going to give me a little bit of an electric field. I'm going to say, whoops, I'm going to say DE. And the first thing I got to recognize is that my electric field, my net electric field, is equal to the integral. And let's have a look. It had KE in it. It had DQ in it over R squared. And we had R hat. But, you know, we know the direction this is going to point, don't we? Because we use symmetry. So I don't need to worry about the vector bit. I can say this simplifies to E net is equal to the integral of KE dQ over R squared. And the problem is I have no idea how to do that. I have no idea how to integrate. What's varying? What is the thing I'm varying? This is my R. What are the thing am I varying between my limits? What starts off small and gets bigger? R. So I'm trying to integrate 1 over R squared with respect to Q. I don't know how to do that. So I either have to change my R's into Q's or my Q's into R's. And it turns out it's easier to change my Q's into R's. So I literally, this is the physics bit. I say, well, hold on. That's a little bit of charge. In fact, this is important as well, so I'm going to change colors. And we're going to go to a nice purple, because this is really regal. A little bit of charge. And my slice has a little bit of width. So I'm talking about that there. And I can say that my little bit of charge is equal to the little bit of width times how much charge per meter, the linear charge density. Yep. I know it's 9 coulombs, I know it's a certain length, and I know it's uniform. It says it's uniform. So my dq is equal to dr, and my linear charge density, well, it's how much charge I have. How much charge is there on this rod? You give me a letter, don't give me a number. How much charge is there on this rod? I'm going to call it big Q. And what should we call the length of this rod? We're going to call it L. Okay. Q's a constant, isn't it? L's a constant. For this problem, it's going to change from problem to problem. So now I take that and I substitute it in here. And I say, well, E net is equal to the integral of KE over R squared. and then I'm put down Q over L dr. Oh, now I'm getting somewhere, because I can do 1 over r squared with respect to r. I know how to do that. So now I say, well, E net is equal to, let's take out all the constants, Ke, Q over L. Let's leave behind everything that's not a constant, 1 over r squared dr, which equals, let's say, Q over L times Ke, just to make it look a bit nicer. And that's the integral r to the minus 2 dr, which equals Q over L Ke. What is that going to be? Let's use our power rule. Increase the power by 1 and put it in the denominator. R to the minus 1 over minus 1. So E net is equal to Q over L Ke. Now let's have a look. Let's put that, well, what are our limits? Our limits now. Our big limit is, where's my slices end? There. And how far is that away from my point of interest?
7 plus 3, 10.
There's my point of interest.
Oh, 9, 6.
This is plus 1.
6.
That's plus 7. That's 6. And what's my smallest limit? How far is 3 away from 1? 2. So this is going to be minus, what's that going to, oh, I'm sorry, which equals, well, let me rewrite this. Q over L Ke, what is it, minus 1 over R. Is that right? Yeah. This is going to be minus 1 over 6 minus 1 over 2, which equals Q over L Ke. What does that work out to be? Minus 1/6 minus minus a half is minus 1/6 plus 3/6, which is 2/6. Agreed? Let's put all our numbers in now. Let's have a look. Q is equal to 9. Ke. 9 over, what's my L? How big is my L?
4.
7 minus 3 is 4. 9 over 4 times 2 over 6, which equals 18 over 24 Ke, which equals 0.75 Ke. And what have I forgotten? Units. What would be newtons per coulomb? So that's the skill.